Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at the derivative of log functions. Now, log functions are no different in that their derivative comes from this formula here, first principles. So this is basically the definition of a derivative. Now, before we start using this, we're going to need to look at this formula here, which actually isn't new to you either. We learned about this when we're doing compound interest. This kind of looks like what you multiply the principal by in compound interest, 1 plus the rate to the power of n, where n is the number of compounds. Now, when we looked at compound interest, we found there was a pattern. The more frequently the interest is compounded, that basically means it's recalculated. The more frequently the interest is compounded, the more money you have. But then we found if we keep making the compounds more and more frequent, the amount of money you have actually reaches a limit. If we made the compounds so frequent that you were compounding continuously, the amount of money you have reaches a limit. And that's because this thing here reaches a limit. Now, we don't really need to prove this. You can just look on your calculator. If you start putting in really large values for n into this formula, as n gets larger, this gets closer and closer to the number 2.71828 and so on, and we know this as the number e. So with a bit of trickery, I can replace n in this formula by 1 over k. So if n equals 1 over k, that of course means 1 over n is equal to k. So what I'm going to do is rewrite this. So it's going to be 1 plus k to the power of 1 over k. Now, as n approaches infinity, so n gets larger and larger, looking over here, we get 1 divided by a really large number. That will give us something close to 0. As n approaches infinity, k must approach 0. So it turns out that this thing here will also approach e. As k gets closer and closer to 0, this thing here will approach 2.71828, which is e. And we are going to need to use this when we actually come to our differentiation. So I'm going to get rid of all this working out, so please pause and copy down if you need. So let's actually start the differentiation. What we're going to do is let fx be the natural log of x. We're going to differentiate it using first principles. So the derivative is the limit as h approaches 0. So if fx is natural log of x, f of x plus h will just be natural log of x plus h, and minus fx, which is just natural log of x, all divided by h. So for our next step, we're going to combine this into one log, because we know from log laws, when you subtract the logs, we just divide their powers. So now I'm going to make this a little easier to work with. I'm going to move this 1 over h to the front, and I'm going to rewrite this. X divided by x is 1, so it'll be 1 plus h over x. So this would be really tricky to try and understand what happens as h goes to 0, because this thing here would go to infinity, it would just get larger and larger, but this thing here would get closer and closer to log of 1, which is 0. So which one's going to win? Is it going to get closer to infinity, or is it going to get closer to 0? We don't know. What we're going to do is make a substitution to make things a little easier. So I'm going to make the substitution k equals h over x. To make things a little easier. Another way to write this is, of course, kx equals h. Now, as h approaches 0, this thing here will also approach 0, because 0 divided anything is 0. So I'm now going to put this substitution here back into this formula. So I'm going to write everything now in terms of k. So as I said, as h approaches 0, k will approach 0. So if h is k over x, 1 on h is just 1 over kx. So when I come to the log, I have h over x equals k, so this will be the natural log of 1 plus k, which makes things much easier. So what I can do now is write this as 1 over k times 1 over x. So note that the limit as k approaches 0 has nothing to do with 1 on x. So I can actually bring this out the front. So then I've got 1 over x times the limit as k approaches 0 of 1 over k, because 1 over x times 1 over k equals 1 over kx. And then I've still got log of 1 plus k. So now I'm going to use another log law. If we have a constant at the front of a log, what we can do is move that and make it a new power. So I've just moved the power up here. Now this helps me immensely because we worked out before that as k approaches 0, this thing here approaches the number e. So as k gets closer and closer to 0, this approaches 1 over x times the natural log of e. But we know the natural log of e is just 1. So this is just 1 over x times 1, or 1 over x. And that's why the derivative of natural log of x is 1 over x. So what about logs of other bases? Well, we can really simply use this identity here and the change of base rule. So we know the change of base rule is log a of b. I can write it as natural log of b, power on top, over natural log of a, base on the bottom. So if I want to differentiate something like y equals log of a different base, log base a of x, that's the same as differentiating natural log of x over natural log of a. So making this easier to work with, I can write it as 1 over natural log of a multiplied by natural log of x. So when I come to differentiate it, it's nice and easy because of what we went through on the previous slide. The derivative of this is just 1 on x. When you're differentiating a constant times a function, you just differentiate the function and times it by the constant. 1 on ln a is just a constant. So the derivative is just going to be that constant, 1 on ln a, multiplied by 1 on x. Or if you like, 1 on x ln a. How easy is that? All right, thanks so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.